Well, I see we clearly have a social side of the lecture and an antisocial side of the lecture hall. How can we make this vast room feel more personal? We will occupy one side of it. I'm totally with you guys on that. I love it. So I'm subbing for Mani for just a few minutes. He's had an empêchement, so we can't quite get here. So we're going to start talking about optimization. So optimization means finding maxima and minima of functions. What's the smallest value the function can take on? What's the maximum value the function can take on? So you can imagine if you were trying to manufacture something, you would try to optimize over the variables at your disposal, investments in machine, labor costs, etc. How can I minimize the amount of cost it takes to develop something? You can also think about maximization. You want to maximize your success in life. How would you allocate your time in Rob 101, Rob 102, future courses, spend time selecting your area of study, balancing that with your mental health. If you could write down functions for those things and then just go through and optimize them, that would just be amazing. In engineering, so as Mani gets set up, yeah, go ahead and get your laptops set up. Yeah, so we're going to emphasize this argmin function, which we have seen in the course. So our function will be a scalar. It will take on values in the reals, but it depends on many different parameters, here m. And remember, x star is the argument of the minimum of the function if f applied at x star is the smallest value that the function takes on.
One common question is that a function in Julia, or is just the way we write it, not coded necessarily like that?
So the question from one of the less well-achieving, one of the students in the class who's turned in no homework so far, is argmin a function in Julia? And the answer is no, but there are packages that help you calculate argmin. And what Mani is going to show you in this lecture is how to to look inside the black box of what these actual packages are doing. And so Mani will come up here in just a second to get things going. Come on. Well, why can I not shrink down? Yeah. Come on. There we go. So one thing you can use it for, and we'll talk about this in lab tomorrow. So there's the perception package on the Cassie robot that runs around. This is an image that shows a camera, a view of the scene. This is walking out of the Double E building up towards Beale Avenue. And the green lines are LiDAR scans. And you can see here, the LiDAR and the camera are perfectly calibrated. You can see exactly the curb lining up in the image, and you can see other points that are lining up on the pole. So this means when I try to merge the camera data with the LiDAR data, I now have a really great 3D version of the world, with the camera being 2D information, but each of these LiDAR points gives me X, Y, Z, and so now I have a 3D representation. And here is a poorly calibrated camera and LiDAR, and you can see the curb is over here when it's supposed to be over here. So there's a lot of ways that optimization can be used. You ready to come up, Mani? I mean, I'll give it to you any time. But when you think about functions and you're trying to find maxima and minima, when it's just a scalar function like this, or maybe it wobbles a little bit, you kind of say, well, I'll just graph it. It's kind of obvious where it is. In machine learning, Monty, these, for example, the neural network that learned to play Go so well, AlphaGo, it has about 1 million parameters or even more.
More,
maybe more, okay? How do you optimize over 10 million parameters, okay? This is a conceptualization of what a cost function on a neural network looks like. And what Monty is going to be showing you is how you can start on one of the ridges and descend systematically to one of the minima, okay? So that's the whole idea. When it's scalar, you can just do a graph and just read it off, okay? But when it's much more complicated than that, you need a systematic method. And with that, Monty, you're back, you're in full swing. I'm going to unplug here.
Modern controllers, right?
Hey.
Quadratic programming.
So, hope I didn't mess things up too badly. Oh, you need the mic.
I need to be able to speak for myself.
No, everything goes through me.
It's a challenge of an assistant professor. Thank you for the introduction. Okay. I think you can see my screen on Zoom and here. Right? Okay. So I'm really glad we get to talk about optimization in Rob 101. And I always wanted to prepare these lectures, but there is no time for these topics in my grad course. But the irony is that the students are uncomfortable enough that I should teach them again. So, talking about optimization in Rob 101 is one of the best things that can happen. Because a lot of real-world problems are, in practice, solved using optimization. Machine learning, robot perception, calibration, finding the transformation between multiple sensors, modern controllers for flying robots, mobile robots, self-driving cars, they all use optimizations for finding some quantities that we'll see what to call them. So mathematics usually helps us to describe the physical phenomena, pose engineering problems, and solve them. It provides a framework for us to formulate our problem. And we're going to see how, in practice, these topics gets connected to linear algebra. Whenever we actually solve something, we're dealing with linear algebra. Although initially it might not look like that, but it boils down to using algebra. And we're going to learn what do we mean by optimal. The notion of optimality is something that we should discuss. So hopefully we're going to make you comfortable with this notation. We want you to think about argmin as a tool that you know you have it and you can comfortably use to solve a problem that you define. We want to talk about extrema of the function. Extrema are minima and maxima of your function. And we want to find out what is the maximum rate of growth. What is the natural direction to follow? And that will lead to a very popular algorithm called gradient descent. Before that, I'm going to define a few terminology. These are the standard terminology in optimization and math. And it's good to know them because we try to formalize as we move forward so you can read documents, textbooks, papers, and be familiar with the terminology. So it's convenient to define something called normal. And the norm ball is nothing but simply, for example, for 2D, you have a center, right, xc, and we're basically saying then pick a radius, and every point, right, that has a distance of r some real number, right? R some positive real number. Call this a norm ball. Basically, it's a neighborhood, right? Pick a point, xc, that's the center, and define a neighborhood. In 3D, this is going to be a ball, right? In 4D, I don't know what you want to call it, hyperbole, hypersphere. So it works. So that using the norm, the notion of distance, we can define this neighborhood. So whenever I am, this ball will define a neighborhood. Some terminology. The function that we want to optimize, we can call it our objective function. We might want to minimize or maximize. We usually write minimize, we'll see in one of the examples, because minimizing f of x is the same as maximizing negative of f of x. So then it doesn't matter. It's the standard terminology to write minimize. You can also write min. You can just, instead of minimize, you can write min. So you can define your program, it's also called a program, or problem, like this. Minimize f of x. F of x is your objective function. Or you could call it a cost function. If you're maximizing, you can call it reward function. Or again, if you're minimizing, you can call it regret function. It's an endless name that you can come up with, right? Objective function is very neutral and standard name. And the variable that you solve for, which is a Euclidean vector, we call it decision variable. Decision variable or design variable is the variable that we are searching for, right? We want to do a search within this optimization problem such that find the optimal value of this decision variable that minimizes the objective function. So when you write min of objective function, you don't write, there's no equality, right? But you can write it in this form. When you explicitly want to mention that the argument that comes out of this problem is this x star, this optimal decision variable, right? So it's perfectly fine to use any of those, right? But when you use this equality sign, make sure you use argmin, right? Do not write x equals. That does not mean that. So when you see this, now you are looking at an optimization problem. That's very standard notation. Again, you can write max of f of x, but this is equivalent to writing min of negative of f of x. So a lot of optimization packages, they don't have maximization method. It's just minimization. If you want to maximize, just multiply your objective function by a negative sign. Now you're maximizing, right? So you still call minimization. The decision variable that we solve for is globally optimal if for every possible x that you can find, right, your objective function gets the lowest value for the entire set of possible values that the decision variable can take, namely here Rm. It is a local minimum if within a ball of radius r, right, within a neighborhood, wherever you are, within a neighborhood, if it gets, your objective function gets the minimum, obtain the minimum value, then that's x star is a local minimum. So this notion of local and global are very important. We often use the same notation even if it's not unique, because local minimum is not unique. You can have different minimums in different neighborhoods, whereas global is unique, or if it's not unique, any other global minimum is the same as what we have. So but in practice, we just don't really care. We just write the optimization function and solve for a local minimum. We'll talk about it when local minimum becomes a global minimum. That's very important. So that's the terminology that we will work with and we use. Here an example. Imagine your objective function is cosine of 3 pi times x divided by x. Tell me local minima and maxima in this, and I will mark it. Here, local minimum, right. This too? This as well, great. So there's a neighborhood, right? The objective function obtains the minimum value. It is the lowest. What about maximum? The opposite peaks? That's a great question. What are the endpoints? Well, these are local maxima. It is true that this can be, in principle, it can be a maximum, right? And in fact, the global maximum is here. This is a global maximum. And this is your global minimum. And this is your local minimum. So you can have many local minima. So the same concept extends to higher dimensions. It is exactly the same intuition, right? There's a neighborhood, we search locally, and the function will obtain a minimum in that neighborhood. Now, when our local minimum or maximum, minimum in this case, is the global. So there's a special type of objective function that no matter where you start your search, you can find a global solution. And these are a class of convex function. So because of that, we want to look into, understand what is the structure of convexity. So we call the domain of a function to be convex if you consider graph of the function, the blue line is the graph of my function. If you pick any two lines and connect any 2 points and connect the line, it will not go through the graph of the function. It will stay inside this ball that you see, right? No matter where you pick, you can move these 2 points. The line is always inside, right? This shape. So that, graphically, that means the function is convex. Algebraically, that means that we'll pick two points, x1 and x2, and interpolate between x1 and x2 using a variable like theta between 0 and 1, right? When theta is 0, we are at x2. When theta is 1, we are at x1. So as it changes between 0 and 1, we can move between x1 and x2, interpolate. Now evaluate your function as you interpolate. So what happens when you interpolate, your function varies like this, right? You're going to move from one point to another. And this is how you evaluate your function at the interpolation. But if you interpolate your function between x1 and x2 like this, right? This will be this red line. So the function is always below that line, that red line. So that's the definition of convexity for a function. It doesn't have to be 2D. It's true for arbitrary dimension, Rm. Then, if you find any local minima, right, that's your global minimum. So it is always preferred to formulate a problem, optimization problem, that is convex. But as you can guess, most of interesting problems in practice are not convex. Another way to think about this condition is that if you do the linear approximation of your function, the tangent line at any point, it is always below your function. If it's convex, there's no way you find the tangent line and that is above your function. That's the meaning of this second item here, first order condition. We're going to talk about a very important condition. Now, the idea to optimize our objective function is to come up with some conditions that the optimal solution should satisfy, right? Now, much of these results come from calculus, so that's the importance of calculus. But you will see, we can just go around it without diving into the calculus. We can still learn how to solve optimization problems. So if you plot the tangent lines at different points, you will notice that whenever you have a minimum or maximum, the tangent line is horizontal. Horizontal tangent line means that the slope is what? Zero. So if my tangent line is parallel to the x-axis, that means the slope is 0. So it looks like, empirically here, we have verified that the necessary condition for this point, right, or this point here, to be a local extremum, because it can be maximum too, this is still true, is that the derivative or the gradient, because the function can be multivariate, must be 0. Now, why this is necessary? Why? If you want to be really picky, then I'm calling this first order necessary. What does it mean? Why? I could just write that the condition, right? And I would get away with it. So first order, it refers to calculating the first derivative of objective function. Okay, so the first order terminology here means that I am calculating the first derivative of my function. Next time we will talk about second orders. Necessary because, well, we have observed that this must be true, but there might be some other points that satisfy this condition, but they are not necessarily minimum, right? So it's not sufficient. One example. So I can come up with one counter example here, right? This is a turning point. right, of my function, you can get a slope that is 0, but it's neither minimum or maximum. None of them, right? So you can look at higher order derivatives, and that's what we learned in calculus. We're not going to talk about it today. On Wednesday, we'll discuss it. So it's necessary because it's not sufficient, but if that point is your minimum, definitely it should satisfy. It must satisfy this condition. First order because we calculate the first derivative. Example, let's verify what we have learned. Least squares problem was the problem of minimizing the norm of a linear system ax minus b, right? This was the least squares problem. From calculus, you can calculate the exact derivative, so not worry how to do it. You can either go to, I think I told you before, you can put a hyperlink for you. You can go to this website and do it. Type your problem, it will give you the gradient, right? For example, I'm going to type here a times x or your alternative is that find a friend who's good at math. Be nice to that friend for a while. Then at some point ask, can you calculate this derivative for me? Usually it works. If you like to be independent, find a website. All right, so for the first part, I need to add a transpose. Oh.
Underscore instead of a
That's, oh, again. Third time and I'll be fired. Okay, so A is a matrix, B is not a scalar. B is a vector, X is a vector. Now, we want to take the derivative with respect to X. Now, these are vector matrices. You can learn it at some point how to do these things. It's not super complicated, but it's not going to be part of your curriculum even in the first time you take calculus, probably, to calculate matrix derivatives. But anyway, your derivative is 2 times A transpose times A x minus B. You can distribute A transpose, right? You get A transpose times A minus A transpose times B. Now you see that we have 2 because this is a quadratic function, which motivates this 1/2 here. It is purely because of the beauty reason. I don't want to see that 2 in my gradient. So I'm going to put 1/2 in my objective function. Which brings us to this point that minimum, if you minimize your objective function, right, the solution is the same as if you multiply your objective function by a positive number. It does not, scaling your objective function will not change the solution of your problem. Of course, it cannot be negative because then you change the minimization to maximization. So take the derivative. The necessary condition is that the derivative must be 0. Set the derivative to be 0, you get the normal equations back. So all the things we talked about, arriving at normal equation in algebra, you could prove it like this using an optimization problem. And then the rest of the story is what you know. LU factorization or QR and finding the solution. You might have noticed that I am using this symbol that I use for global solution. We do not know at this point this is global, but it is, because next time we can show that this problem also satisfies a second order condition, which proves that this is also the global solution. For the second order, we're going to look at the curvature instead of slope. And this is just a reminder that you should know already that in least squares problem, A is a tall matrix, right? We have more rows than columns. A is full column rank. All the columns of A are linearly independent, so that A transpose A will be invertible. So we just verify this necessary condition, it works. That's for the familiar least squares problem. Okay. Very important claim. I'm going to claim every direction that is a descent direction. Every direction, if you want to search for the solution, right? Optimization essentially is a search problem. But our functions are continuous and differentiable. So we can use continuity of the problem to come up with nice algorithms. It's not a discrete search. Every direction that causes your objective function to go down, you reduce your objective function, is called a descent direction. A direction is a descent direction if you take the dot product of your, I'm using inner product, the bracket, because I like it. But you can also, this is the same thing, right? And I remember we defined the gradient to be a row vector, right? So this is basically the dot product of two vectors. So the dot product of your gradient and the direction, the delta movement, delta x, if it's negative, then that's the descent direction. Now let's prove why that's the case. To prove this, it's sufficient to calculate a linear approximation of your function. So at the next step, f of x k plus 1 equals f of xk plus your gradient times, right, delta x. This is linear approximation. I am just defining your gradient to be right? And delta x is what we defined last time to be a delta movement from xk, okay? That's what we used last time as well. So if I move f of xk to the left side, and I define, just like x, right? F of xk plus 1 minus f of xk to be a delta f. So the delta f is basically the dot product of my gradient times delta x. This is very important. Some people take this as the definition of gradient. In calculus courses and more advanced courses, you could start from here and say this is the definition of the gradient. And when it's continuous, the delta f is basically, they call it differential of f. So obviously, if I want my objective function to decrease, the delta f should be negative, right? Does that make sense? I want f of x k plus 1 to be less than f of xk, right? Because I want to minimize it. So that means that delta f, if I subtract f of xk from both sides, well, then this should be negative. And then take the approximation as faithful. It's roughly describing your function, right? As equality. And then, well, the dot product of the gradient times delta x should be negative. Both sides should have the same sign. So therefore, this gives me this condition To find the descent direction, the dot product of the gradient and delta x search direction should be negative. Now you might have a very good question that what is a good search direction, right? What is a natural direction to follow? Is there such a thing? Because search direction can be anything. You can generate directions randomly, and that's perfectly fine. But can you think of one problem with random direction? If every time I generate a random delta x, and then try to follow that direction to minimize my function, what's wrong with that? Can you say it louder? No, there is a direction. Random is fine, right? I can write an algorithm, draw a random direction vector, right? First move here, I'm somewhere. Next time I'm moving here. That's perfectly fine. But what's wrong with it? Look at the title. Is the random direction the descent direction? Not necessarily, right? What if I'm maximizing my function now? Anything can happen, right? So we want a little more principle, right? That's just too random by construction. So we are after a natural direction that is also computable, right? It's not too hard to find. So again, there is such a direction in this problem, and it turns out that's the gradient. Gradient is the natural direction to follow, because that's the fastest ascent direction. It's not the fastest descent direction. Then you might ask why. There are several ways to think about it, but I had to come up with something that you don't need calculus, right? So that's basically the pain-free version of the explanation. So you need to look at the contour plot. Contour plot, if you've seen maps, topography maps, right? Grab your function at every height here, right? Define a plane that will cut your function, right? It'll give you a curve. Do this at many heights and project all of them onto the XY plane, the plane from top view. That will give you the contour plot, right? So these are intersections of just horizontal planes at different heights. And you can, of course, choose what resolution you want to generate this graph. You have the option, right? And these curves that you see here, these are called level set. So it's a level in the left plot, right, that the plane will cut your surface. What do all the points on this curve have in common? In one red circle that ellipse that I'm showing in the right graph, what do they have in common? That will be very important because that's the lifesaver. Well, do you agree that my function is the same, is constant along that curve, right? Because by definition, I'm cutting this function surface using a plane that has a constant height. Whatever is the intersection, which gives me this ellipse, that means that my function is constant. It's the same value at any point on that curve, okay? Which is the definition of level set as well. Now, in the other ellipse, my function has a different value, but along that curve, my function is constant. Okay, so now, if that's the case, imagine I move from one point. If I move from one point here to another, right? I make a delta x movement in that direction. But my function is constant, right? A delta along the curve for 2 points that defines a vector that is tangent to that curve will not change my function. In other words, the delta of my function is 0 because it's the same, it's constant. Now, from linearization, previous case, that defined the descent direction, I know that the delta f is the dot product of the gradient and an arbitrary delta x, right? Well, therefore, this must be 0. When the dot product of two vectors are 0 and they are not 0 vectors, they are orthogonal. So this proves that the gradient is orthogonal to any point. Basically, it is orthogonal to any vector that is tangent to these level set curves. And this figure is numerical verification. You can look at it in the book, read more about it. Numerically, you can define your function, define the level set, calculate the gradient, and visualize the gradient at that point. You will see that it is orthogonal. But it's pointing to the shortest path that you can move from one level set to the next one, right? I'm moving from one level set to the next one. So orthogonal movement is the fastest direction that you can increase your function because you can see the minimum is the center. And as I move orthogonal to these curves, I can increase my function as fast as possible. Now, if this is a valley, right, and that means that the fastest way to the peak, right, is following the gradient. But probably that's the hardest path as well. You need to climb a very difficult direction. But regardless, that's the direction that we can maximally increase our function. So the negative of that will be the direction that maximally we can decrease our function, right? So that leads to very important discovery that if I pick my delta x instead of random to be positive or negative of the gradient, given that I know these two directions are already the directions of maximum growth and descent, I can get basically the fastest ascent direction and the fastest descent direction. Now, if you plug in delta x into the dot product, what you get is basically the norm squared of your gradient, which is always positive by definition. And for the second case, when we pick delta x to be the negative of the gradient, which is what we're talking about, you get negative of the norm squared of the gradient. It's always negative, right? You remember our claim that we proved that the descent direction is a direction when the dot product of the gradient with that to be negative. So if delta x is the negative of the gradient, always this condition is satisfied. It's always negative. So it's always a descent direction, and we know it's the fastest descent direction. So that makes it a natural choice for the search direction. And that leads to the very celebrated algorithm called gradient descent. So it's a minimization method by choosing the gradient as your descent direction. You can have gradient ascent as well to maximize. But as we talked, it's enough to define the minimization program. So start with an initial guess, x0. Evaluate your gradient. If the norm of your gradient is 0, the algorithm is converged, because that was the necessary condition, right? The derivative to be 0 vector is the necessary condition for the local minimum. So we will stop at this point. Otherwise, update your decision variable using this rule. Wherever I am, xk plus a delta x. Right? But the delta x is negative of the gradient. So you see that negative sign. And delta x is negative of gradient. Now, what is alpha? Just like root finding, just one giant step using the gradient, that might be too big of a step for the algorithm to converge. So in practice, to make it work, we need to define something called a step size. Now, we will consider it fixed, and in the larger scale problems, it's usually fixed and it's a very small value. But if you take a serious course on optimization when you want to dive into every detail, you can actually compute this using a method called line search. And a lot of packages, they also compute this. So you don't need to use a fixed value. Now, despite the fact that it's called line search, it's not actually line. It can be a cubic polynomial or other models, okay? So it's a mini optimization inside your optimization to find out the step size. It's very important. And we repeat this process. Okay, so this basically is very simple. It's the gradient descent algorithm. What's the beauty of this algorithm? What do you think makes this algorithm attractive that so many people, basically the entire literature of modern machine learning is on this algorithm. Different variations of this for training neural networks. Why do you think this is worthy of so much attention? Random thought, maybe? Maybe because it's simple? First of all, it's very simple, right? If I only can evaluate my objective function and have access to the first order derivative gradient, right? I can solve an optimization problem. I don't need anything else. And in fact, within this algorithm, I don't even need to evaluate my objective function. I only need the gradient. There's no place in this algorithm that I'm evaluating the objective function itself. So that makes it interesting, because now for larger scale problems, it's very difficult to evaluate higher order derivatives. Computationally it becomes intractable. And this simplicity for a search algorithm has made it very attractive for larger scale problems. So they would use higher order methods like second order, but there are concerns for tractability. Okay, so let's go to the Julia notebook now and look at the code. So before we leave, next time we will talk about second order method. That will be the application of Newton's root finding for optimization. This was the first idea, first order method that leads to gradient descent. So you will have access to the notebook from Canvas. I uploaded there. I added some background just to refresh if you're working directly in the notebook. We're talking about unconstrained problems. There is no constraint. Constraint is when I say, for example, my decision variable must be positive or must be between 1 and 2, right? That's a set of constraints. We do not have constraints. Our vector can be anything in Rm. So that's the unconstrained optimization. So gradient descent is a solver for unconstrained optimization. So we define our program or problem as by writing minimum of objective function f of x such that x belongs to Rm. You could write it maximize, right? Max of f of x. But maximizing f of x is the same as minimizing negative of f of x. So we don't talk about gradient ascent here. We just talk about gradient descent. To reiterate the algorithm, start with an initial guess, evaluate the gradient. If the norm of the gradient is 0, stop. Otherwise, update your decision variable and repeat until convergence. And as you can guess, there is no guarantee for convergence. So you might pick a step size that is too large, and the search will continue forever without convergence, or it reaches the maximum number of iterations. You have not found a solution at that point, right? Let's look at the first example. I have a quadratic function, x transpose times a matrix A times x. A is a specific fixed matrix. You can calculate this quadratic, which will give you a polynomial. And that's our objective function. We want to find x star that minimizes this function. Now, this function, the domain of the function is 2D, therefore we can visualize it. If I visualize this function in Julia, is this function convex or not? It is, right? It's a quadratic function. Quadratic functions are convex. Clearly, the minimum is at 0, right? If x1 and x2 are 0, that's where my quadratic function takes its minimum. So that's the solution. So we know the solution. That's a test problem. We want to see if our algorithm works well. It's easier to see the convexity and the minimum when you visualize the contour plot. So I'm generating the contour plot, right? So you can also generate for any function that's possible. That's why I'm giving you the code. It is as simple as just one line. You can generate a contour plot of your function. So clearly the point 0, 0 here is the global minimum. Now let's implement the gradient descent. We need to start with an initial guess. X0 here, I choose to be -1 and 2. Now, if you remember from last time, we used forward diff, automatic differentiation, as a new package to calculate the Jacobian for us. If you have it already installed, you don't need to install it. You can just load it. If not, make sure to add the package first, and then include the package using forward diff. Next, I am defining my objective function. F1 is my quadratic objective function. And the next block is the gradient descent algorithm. So I'm defining my initial guess, then I'm defining the step size alpha. Here is 0.2. I'm using a convergence threshold as before, delta. My maximum iteration is 100. I have a counter n equals 1. And my decision variable, this shouldn't be root, because I copied from my previous code. So this should be your decision variable. So let me run this actually. Now make sure you're using Julia 1.6. I had some problems running the plots, although it was working last year, but with Julia 1.4, it wasn't. So I upgraded to Julia 1.6, the latest you find on the website, and problem disappeared. So I'm also not going to look back. Right? First rule of engineering, when something works, do not touch it. Let it work. So make sure you're using the latest Julia. The stable version is 1.6.3. And I think, yeah, that's the one on IllumiDesk. So you should be fine. Okay. So the algorithm is like this. While the number of iteration is less than the maximum number of iteration, I'm calculating the gradient. Okay, this is the gradient of f at xk. Now, the interface, the function that I'm calling is gradient. Last time we used Jacobian, right? Of course, you can use Jacobian for gradient as well, because gradient was a special case. But it has a different routine. You cannot use Jacobian. So the way it's implemented in this forward diff package is that if you want a matrix Jacobian, you call Jacobian. If you're working with gradient, a vector, call the gradient, right? And if it's a scalar, I think you need to call derivative. So that's why you see now this is not Jacobian, it's a gradient. But anyway, you pass the object of your function and the point you are, xk, right? This is basically xk. That was the first step, right? What was the second step? Second step was to evaluate the gradient, but also check if the norm is 0, right? If the norm of g, the gradient, is less than that threshold 0, in practice, of course, it's not going to be perfectly 0, then we are converged. The algorithm is converged, and then we break the loop. If not, else update your decision variable. This is basically xk plus 1 equals xk plus delta x. But delta x is negative of alpha gradient of f. And this is g. So it's going to be x equals x minus alpha times g. Then I count 1 for the iteration, and this continues until convergence or hitting the maximum iteration, maximum number of iterations. Now, I ran it yesterday, but I think it takes unusually longer when I'm in class. I don't know why. The first block is still running here. Now, if you run it, you will see that it takes 43 iterations to converge. As expected, the value of the decision variable, right? So almost 0 because my delta, the threshold was 1e negative 9, right? If you make that 1e negative, I don't know, 15, right? This will be, should be less than that. But based on the threshold that I chose, this is my 0. So the algorithm could find a solution of the optimization problem. So you can see that it's very simple. In one loop and a few lines, you can write your own solver. So if you use an optimization package, it's usually something like this, but probably they also calculating alpha each time, to not keeping it fixed, to evaluating each time to be a optimal step size. Okay. We have another example, but let's see if we have any questions about anything we talked so far, including the code.
Yeah, there's a question on chat is, would the gradient be negative and hence your negative of the negative is a double negative and it's not really necessary, so there's confusion on the direction of the gradient.
The gradient as a vector can be negative, right? That's not a problem. Relative to the shape of the function, right? It shows the direction of fastest growth. Now, it is not relevant that if I'm moving in the negative direction of x-axis, right? That's got nothing to do with whether my function is increasing or not. It could be the case that if you follow the negative direction of the x-axis, then your function is increasing. So it doesn't matter if the gradient is negative or positive. Just think about it as a direction that shows the fastest growth of your function. And therefore, its negative is the fastest descent direction. Looks like everybody is an expert in gradient descent. If you're comfortable implementing it, there's no dark spot in this algorithm. Anything you would like to know that perhaps I didn't explain?
Time to do it.
Yeah, so do it. Find something more complicated. The algorithm should be the same, right? We had to wait so long to implement this. We had some hand calculation optimization in high school, and then I took a master course on optimization, and then finally somebody was talking about optimization. It was really unnecessary to wait that long. Okay, so I think what we're doing is bad for business of grad schools. They have to upgrade their materials. Okay, so next example. Let me clear this. Now, also notice that I didn't call the gradient to be the best direction, right? It's just the natural direction, fastest growth. Please do not use that word because it doesn't mean it's the best direction to follow. It is just the fastest growth and negative of it fastest decrease direction. Much of what has consumed the research communities to find the best direction at each step is the fact that it is fastest, but fastest looks greedy. Like at any point I see what's the fastest growth and I'm following that. That doesn't mean it's the best. What do you mean by best? Right. Best, you can consider it best is the direction that guides me to the solution in less number of iterations, for example, right? This algorithm has a known problem of jittering. When you get close to the solution, it can, because you're greedily following the fastest at each time, you can just jump around, right? Do a zigzag near the solution. So there is a lot more into it, but nevertheless, this is the first encounter should be like this. You use the gradient descent. So it's not the best, it's the fastest.
Yeah, it's a little bit like empty calorie sugar. Really fast uptake in energy, but it doesn't last, okay? Sometimes the gradient, really fast decrease in your function, but it doesn't last in that direction. So that's just a...
Yeah, that's a good analogy.
Analogy. Sugar
Right.
Versus
spice.
Potatoes and starch and pasta.
So the analogy is that you use sugar, you get your energy quickly, right? It's not going to last. You eat a fruit or something, fructose.
Pasta.
It gradually is going to increase release the sugar in your body, and it lasts. So especially we are looking at the linearized version of our function, right? That doesn't mean when you move, that linearization is valid. So it's a very narrow way of making decisions. Wherever I am, find the fastest way to decrease my functions and then follow that. Next time, do the same, do the same. This is like a greedy behavior, which is why it's not the best, right? All right, so, and that question was fair. What do you mean by best? Also, you can ask, what do you mean by optimality, right? These are relative notions. The solution is optimal relative to the objective you defined, right? There is no such a thing that universal optimality. You can change the objective function, then that solution could be the case that it's no longer optimal. So up to the problem that you define, that's optimal, okay? So in some sense, you should define the optimality and the best. It is unclear on its own what it means, okay? Second example is a little more complicated. This function is no longer convex. I have here 2 peaks and 2 valleys, 2 minimum and 2 maximum. Besides, this time I want to maximize my function, okay? I'm not looking for a minimum. I want to find the closest peak. So if I'm here, right? I want to go here, right? It's local, right? So if I here, I'm going to go here. Wherever you start, now if you start here, it's not going to go to minimum because I don't want to find a minimum. I want to find a maximum, right? As we discussed, all we need to do, we need to say that my solution is arg min of negative of this f of x. So we multiply the objective function by a negative. Why we do that? Because our previous code is still reusable. I don't have to change the code, right? So you implement it once for minimization and use for both. That's convenient. Okay, so if you look at the counterplot, that makes it clear that there are two peaks and two valleys. These darker ones are minimums and bright curves are the maximum. So I need an initial guess. I pick 1 and 0. So you can change the initial guess later and see the behavior of the algorithm. What I'm choosing is 0 and 1. It's roughly here. This is my x0. So we expect we converge to somewhere here. Okay? If you choose a point here, you will find this one, most likely. Depending on the gradient, right? The gradient probably is pointing towards the other peak. Okay, as usual, I'm going to define my function, calling it f2 this time. And all I'm doing is multiplying it by a negative sign here so that I can minimize it instead of maximizing it.
On the counterplot earlier, you're describing like initial point. Was that, were you describing like that initial guess that in the algorithm? Like taking that initial guess and then depending on the distance of that guess from a specific extra, you'd get that extra.
You're saying that I talked about this initial guess. How do I choose it?
No, actually, I want to follow up on that. What if our initial guess was equally as far away from two different algorithms?
Something we can try, right? If it's initial guess, if it's here, right? That's your question?
No, I meant like if it was
Oh, if it's equally far.
yeah.
Well, don't start there. My advice is that don't start somewhere that you know you're going to get stuck.
Probably the gradient is 0 there.
Yeah.
Okay.
So you don't want to start, and that's a good question, and good point is that don't start somewhere that the termination condition is met, right? At the very least, you can check if the gradient is 0 or not. So probably 0 in this particular function. Remember, for the actual problems, there's no such thing as visualization, right? If it's x10 or 100, you're not going to be able to visualize it. So make sure the gradient is not 0. You can start randomly. You can start solve it for several different initializations, right? And that's the major challenge of optimization when the cost function is not convex. The solution depends on the initial guess. But you can start and see what happens. In this particular case, the gradient is 0 probably. So I define my function multiplied by negative, and I will not change anything in the code except my initial guess. I do change something else, and that's the step size. Try 0.2. It doesn't convert for this one. It doesn't work. It's actually sensitive. So you need to change a smaller value. Again, this is something that if you, in the future, playing with deep learning libraries, like PyTorch, TensorFlow, they call this learning rate. This is the same thing as a step size, and usually you see something small, like 0, 0, 1, or even one more zero, right? It's so complicated that objective function, you need to take a really, really small steps, and it takes it might take days to train your model, meaning finding values of the weights. The weights are your decision variables. Okay, the algorithm is the same. I calculate the gradient this time for F2. I will not change this line because I multiplied my function by negative, right? And after 119 iteration, right? Actually, I did change this too. It's not 100, it's 1,000. So the step size, now you can see the trade-off, right? The step size, when it's small, you need to iterate many times, right? Ideally, you want to take a big step, but big step will cause the algorithm not to converge. So you're constantly dealing with this dilemma of what is the biggest step size at each iteration I can take that's not going to ruin what I've done so far. That's a very difficult question to answer. But we pick it to be conservatively very small so that it works. So 119, the gradient is 0 according to my threshold, delta. We're at 4 point roughly 5 and 0. Let's go back, look at the function, see where that falls. So 4, if this is 4, 5, so 4.5 and 0, right? It's this peak. So I could maximize my function successfully. Now you can go ahead and remove the negative sign. You should find one of the minimums for you. And then you can change the initial guess. As a practice, you can also add another example, right? Add different functions and see how it goes. So that wraps up gradient descent. That's all you need to know. Unless you end up working in this problem, you might want to learn deeper. Otherwise, when you use an optimization package and you call gradient descent, right? You know what's going on inside. You have an idea. It's not black box anymore. And the basic version of it is very easy to implement. So that's the lecture for today. Next time, we will talk about second order method, Newton's method, and hopefully Gauss-Newton method.